So in today's discussion, we will have transmission of heat or transfer of heat. Okay, so let us start. Transmission of heat. Like I said before, the module heat and thermodynamics is done in 4 different sections. First part is thermal expansion calorimetry. Second part is transmission of heat or transfer of heat. Third part is thermodynamics. And the fourth part is kinetic theory of gases. So we'll start with transmission of heat. Now, what is meant by transmission of heat or transfer of heat? Heat is taken from one place to another. Okay, heat is taken from one location to another. This is called transmission of heat. Now, this can be done in 3 different ways. Now, the modes of heat transfer are conduction. Hope you remember this from class 11. Conduction. Number 2, convection. Number 3, radiation. So there are 3 modes of heat transfer: conduction, convection, and radiation. Conduction, convection, and radiation. Okay. So what is the point here? Like I told you, you are taking heat from one location to another. Now this can be done by 3 different modes, 3 different ways. You know, conduction is mode number 1. Next is convection. Third is radiation. Now based on convection, you won't have numericals. Convection, you know, there is no numerical. There is only one equation in convection, but that is not given in NCERT. You don't have to learn that for NEET examinations. Okay. Convection. Radiation, there are a few equations. I'll come back to that later. First, we will see conduction. Conduction is the most important part. Okay. I'll give you a brief idea of these 3 modes. What is conduction? You take a metallic conductor. It is like electric conduction. In electric conduction, who is taking electricity from one place to another? Electrons are the charge carriers, right? Electrons are the charge carriers. So even in heat conduction, electrons are carrying heat from one place to another. Okay, we even have one law called Wheatman France Law. Wheatman France Law, which actually connects electrical conductivity with thermal conductivity. Electrical conductivity and thermal conductivity are related by this equation. K by sigma T is equal to a constant. This is called Wheatman France Law. Okay, Wheatman France Law. That's an advanced level thing, but anyway, you just know this. I was actually trying to compare electrical conductivity with thermal conductivity. Electricity is being conducted on a conductor by way of electrons, using electrons. Similar way, even in the case of heat conduction, the heat is being transported by electrons. That is why metals are good conductors of heat. Just like metals are good conductors of electricity, they are good conductors of heat as well. Okay, and we even have a relation connecting them. K is called thermal conductivity. Ability to conduct heat is called thermal conductivity. Ability to conduct heat is called thermal conductivity. Ability to conduct electricity is called electrical conductivity, sigma. So K by sigma T is equal to a constant. That means if you take a conductor, K by sigma T will be a constant, where T is its absolute temperature. This is called Wheatman France Law. Okay. Anyway, I'm taking a rod here and I'm keeping one end of the rod in a flame. This is a flame. Okay. Right. I'm really bad at drawing. Anyway, this is a flame. I'm keeping one end in the flame, and then the other end is kept in, say, cold water, ice water. Okay. Ice water. So this temperature is like, say, let us assume it is 80 degrees Celsius something. There it is like, say, 10 degrees Celsius, cold water. Then what happens? Heat is transported through the conductor. How? By way of conduction, right? So in this solid, heat is transported through conduction. Convection is not possible in solids. Radiation is also not possible in solids. In the case of solids, only conduction is possible. Electrons are being transported. Electrons carry heat from one place to another. So, and you know, is there any movement for electrons? No, electrons stay where they are. Just imagine this case. 10 people are standing in a row. 10 people, okay? And the first guy wants to transfer a baton to the last guy. Will he have to go all the way to the last guy? No, he just has to transfer it to the second one, then second to third, then third to fourth. Now that way, you know, the last guy would get what? The baton, right? The baton can be transported from the first guy to the last guy without the first guy moving, right? This is actually what's happening here. Heat is being transported from hand to hand. Electrons are not moving, or the particles of the medium are not moving. The particles of the medium are not moving. Only heat is transported. While in convection, the medium itself is moving. Convection, I'll tell you. Look at this. I'll tell you, convection is this. This is water in a tank. Okay. And then you heat it. When you heat it, what happens? Water gets heated, right? Heated up water is less dense. Its density decreases. So that will go up. Heated up water will go up. Automatically, cold water from top will come down. Right. So this is actually circulating water currents. Now this is called convection. You know the heater. If you have a water heater, solar water heater at home, that actually works on convection principle. Solar water heater. Okay. So, or even a heater, no? Heater. Heated up water goes up, cold water comes down, again it heats up and then it goes up like this. So it's a circulating thing. This is actually convection. Or, you know, if you look at a candle flame, look at this. This is a candle and this is a flame. Okay. Why does the flame look like this? Because, you know, the air around the flame is heated. Air around the flame, no? This is a candle, no? It's a lit candle. Okay. And then if you look around the flame, the air is heated up and the heated up air goes up. Now, as it goes up, it actually drags the flame upwards. That is why, you know, the flame looks like this. Understood? That's again convection current. So in convection, there is actual medium movement. Here, you know, medium does not move. Medium doesn't move. Okay. Here, medium itself moves, right? Here, water, when heated up, it moves up, right? Here, the air, hot air moves up, right? Or even at your home, the ventilation, no, that is put on top, right? Why? Heated up air should go up and escape, right? Yes, ventilations are never put, you know, on the floor. It is always put at the top, right? That is because of this, because heated up air has to escape. Then only fresh air can come in, right? Through the door. All right. Anyway, that is convection. In radiation, no medium is required. This is actually an electromagnetic wave, heat wave. Electromagnetic wave, no? Electromagnetic spectrum. You learned that in electromagnetic waves in class 12. There are certain waves which belong to a group called electromagnetic spectrum. In the group called electromagnetic spectrum, none of the waves would require a medium to travel. Light wave, ultraviolet, infrared, gamma rays, X-rays, radio waves, microwaves. There are lots of them, right? And among them is infrared radiations or heat radiations. Heat waves actually belong to that group. No medium is required. So this is the major difference among these three. Conduction. In conduction, there is no transport of medium. Medium doesn't get transported from one location to another. In convection, medium moves. Convection. Look at this, heated up water goes up, right? Or heated up air goes up, right? So medium is moving. Here the medium is not moving. Only heat energy is transported. And then in radiation, no medium is required at all. No medium. Medium is because you've been getting energy from sun over the past 5 billion years by this mode, right? Because there are huge empty spaces between us and sun, right? Empty spaces. Even there, heat is being transported. By which mode? Can't be conduction, can't be convection, because both of them would need a medium. But in the case of radiation, no medium is required. So this is how sun has been giving energy for us over the past 5 billion years, like I said. Okay, so conduction, convection, radiation. So this is usually happening in gases. Radiation usually gases and transparent media. Convection happens in fluids, usually fluids. It has to be a liquid or a gas. And most of the time, conduction happens in solids, even though conduction is possible with any cases. I mean, solids, liquids, gases. Okay, so conduction is the most important of all. And conduction happens mostly in solids, but it can happen in gases and liquids as well. But convection happens in liquids only because medium should move, which can't happen in the case of solids. And radiation happens in transparent and gaseous media. Okay, and we will focus our discussion on conduction now. So we are taking a conductor here. Look at this. That's all about conduction, convection, radiation. You have to write this down. Wheatman France Law. K by sigma T is equal to constant. K by sigma T is equal to constant. And if you take a wire, look at this. This is a wire whose one end is kept in boiling water like this. Kept in boiling water. This is boiling water, which is 100 degrees Celsius, which is at 100 degrees Celsius. The other end is kept in ice water, that is at 0 degrees Celsius. Obviously, heat moves from hot end to cold end. Okay, electrons are carrying heat from one place to another. Now, after some time, something called a steady state is attained. Steady state. Okay, steady state. What is steady state? Initially, the temperature here is 100. Here is something like 90. Here it is something like 80, 70, 60, 50, 40, 30, 20, 10, 0, like this. So there is a temperature gradient as you walk to the right. Okay, temperature decreases as you go to the, where is the hot end? You know, to the hotter end, towards the hotter end, temperature will be greater, right? And as you go to the right, temperature gets reduced. Am I correct? Am I correct? Am I correct? So initially this is like 100. When you put it, this is like 100. After some time, the temperature attains a constant value here, like 80. Temperature attains constant value 70. Temperature attains constant value 60. Okay. So before that, it was like 50 or something, 51, 52, 53, 54, 59, 60. So every cross section of the rod attains a constant temperature. At a constant temperature, this state is called steady state. Okay, you just have to know this. That's it. And if you draw the graph of temperature against distance from hot end, it will look like this. It will be a rectangle hyperbola. That is actually common sense. Temperature. If you draw temperature against distance from hot end, as you increase the distance from hot end, temperature decreases, right? That is seen clearly here, right? Temperature decreases exponentially. Look at that. I'll repeat one more time. What is steady state? What is steady state? Steady state is the state that is achieved when all the cross sections have constant temperature. Their temperature is constant. For example, when you started off, this was like say 20 or something, this cross section. Later on, it increases as time passes, and then later on it settles down at 80. This one settles down at 70, next one at 60, next one at 50. So every cross section's temperature has finally settled down at a constant value. This is called steady state. Don't worry, if you are given a question, the system will be in steady state for sure. Okay. Now at this point of time, if you write temperature again, if you draw temperature again, it's distance from hot end. Temperature is on y-axis, distance is on x-axis. If you draw the graph is a rectangular hyperbola. This is called rectangular hyperbola. As distance increases, temperature decreases. And I have an equation here. This is the most important equation around. dq by dt is equal to k into a into dt divided by dx. This is the rate of heat transfer. This looks like what? This is dq by dt, the amount of heat transferred per second. The amount of heat transferred dq per time per second. The amount of heat transferred per second is equal to k into a into dt by dx. Now, this is the only equation you will see in the whole topic of conduction, dq by dt. dq by dt is equal to k into a into dt divided by dx. Okay. So, this is what? Rate of heat transfer. Heat transferred per second over a cross section. What is K? Thermal conductivity. What is A? Area of the conductor. Area of cross section of the conductor. What is dt? Temperature difference between the ends. What is dx? Distance between the ends. That means distance between the length of the conductor. I'll tell you one more time. I'll write it down here. Look at this. We have a conductor here. This is a conductor. Okay. I'm drawing a little better figure. Right. Look at this. Okay. This end is at temperature T hot. This is a T cold. Okay. Cold junction and hot junction. This temperature is TH, which means hot junction temperature. The other is cold junction temperature. The area of cross section is A, and the length is L. Okay, length is L. Or let us say, okay, L is fine. So, what is the amount of heat transported through this? dq over dt is equal to k into a into dt, that is th minus tc. dt, earlier I wrote it as dt. dt is actually T hot minus T cold. Divided by length. Earlier I wrote it as dx. K into a into th minus tc divided by L. Never ever forget this. This is very, very, very important. Every time they ask questions on this, dq by dt is equal to k into a into th minus tc divided by L. Okay. So where K is called thermal conductivity. A is area of cross section. TH and TC are temperatures of hot junction and cold junction. L is the length. And I'm going to tell you something now. I'm going to write something similar to this. Look at this. You see this? Current is given by voltage by resistance. Am I correct? Have you seen that before? Electric current, right? Electric current is voltage by resistance. So electric current is actually what? Electric current is dq by dt is equal to V by R. So this dq by dt can be called thermal current. So I can call it thermal current, I thermal current. No, this looks like current, right? I thermal current is equal to dq by dt is equal to, I'm making a little bit of modification here. I'm writing this as Th minus Tc divided by L by Ka. Look at that. Look at that. I've just taken this Ka to denominator. I've just rearranged. Look at that again. I'm repeating. This equation is rearranged. Okay, this equation is rearranged. dq by dt. dq by dt is what? Rate of heat transfer. Heat transferred per second. Heat transferred per second. dq by dt is equal to what? I've taken this Ka and put it on denominator. Put it on denominator by Ka, L by Ka. On numerator, I have Th minus Tc. Now look at this. This one looks like this equation. Am I correct? On numerator, we have potential difference. On numerator, we have temperature difference. Temperature difference. Am I correct? Oh, tell me what? Potential difference causes a current flow, electric current flow. Similar way, temperature difference causes a thermal current flow. I can call it thermal current now. Thermal current. ITH. Thermal current. Okay. I'm calling it ITH. Just the way potential difference creates an electrical current, temperature difference creates thermal current. What is on denominator? Resistance. So this must be a resistance, and that is called thermal resistance. Thermal resistance is L by K. L by K. Just like electrical resistance is there, thermal resistance is also there. L by K. L by K. Did you understand this part? Look at this. This is very, very important. I have written an equation for dq by dt. This is rate of heat transfer. The amount of heat transferred per second is K into A into Th minus Tc divided by L. Okay. I just modify this by taking this to denominator, L by K. Now this one looks like what? This is temperature difference, Th minus Tc, just like you have potential difference. And on denominator, it is resistance. So this denominator must be resistance, some sort of resistance. And that resistance is called thermal resistance, because on the left side is current. It looks like what now? Current is equal to voltage by resistance. Now L by K is thermal resistance. Why did we do this? Because now you can have series and parallel combination of resistors. For example, you know, I have conductors like this, one conductor like this, second conductor like this, third conductor like this, likewise. Understood? Okay, there are three conductors. How do I take it? You can take it in series combination. Rs is equal to R1 plus R2 plus R3. Understood? Rs is equal to R1 plus R2 plus R3. I'll show one example. Did you understand this? Oh, tell me what. I'll do this here. So have you noted this down? Tell me. Shall I wipe it? Okay, fine. Right. So we're going to see combination of conductors now. Combination. Series and parallel combination. I'll do one for sample. Right. Series combination. Look at this. I have series combination of conductors. There are two conductors. Series combination. Okay. All right. Look at that. The areas are the same. All right. And areas are same. Lengths are also same. All right. Or areas are different. Let us. Areas are same. Lengths are same. L. This is A. Area A. Okay. So I've taken two cases. What is the equation for combination? This is a series combination. Series combination resistance is what? Rs is equal to R1 plus R2. Hope you remember. Do you remember? Oh, you've been seeing since class 10. Tell me what? What is the effective resistance in series? Electrical. I'm talking about electrical resistance. This is similar, right? Okay, Rs is equal to R1 plus R2. Now tell me, what is Rs? I told you before we started, R is L by K, right? So on the left side, L by K. So 2L divided by K. Why did I take 2L? Because on the left side it is effective. So total length is L plus L, 2L. Correct. And on the right side, for the first one, L by K1A. This has a conductivity of K1. This has a conductivity of K2. Plus second one, L by K2A. Tell me what you get. I can cut A's here, L's here. And what is effective now? I can take 2 by K is equal to 1 by K1 plus 1 by K2. Take the reciprocal. It is what? K will be, if I take LCM, it is 2K1 K2 divided by K1 plus K2. This is the most repeated question here. Okay, right, K1 plus K2. I've taken two conductors, whichever question comes now, you can formulate the equation. There is nothing difficult in it, no? L and L are the lengths. K1 is the conductivity of first one, K2 is that of second one. Area is common to both. You won't be given like equation like this with a different area. Such a question won't be given. Trust me on that. Don't worry. Okay. And thermal resistance is L by K. So I put Rs is equal to R1 plus R2. Rs effective. It is what? L is total length, L plus L2L by K. K is effective. I can call it Ks. Into area is A. For the first one, it is L by K1A. Second one, it is L by K2A. You cut them out and then you get K is equal to 2K1, K2 divided by K1 plus K2. I'll tell you another one. That is for the first one. Now I'll take a parallel combination. Look at this. I take a parallel combination. This is a different question, okay? Look at that. Both have same length, but areas are different. Area is A1, area is A2. Tell me. You have to learn both these as shortcuts, okay? Because they are frequently asked questions. Tell me if you got two different areas side by side, kept side by side. Tell me how you take it. 1 by RP. 1 by RP is equal to 1 by R1 plus 1 by R2 because these are in parallel. They are kept side by side, right? Side by side. So 1 by, tell me what 1 by. Resistance is L by K. So L by K into A1 plus A2. Tell me why. Actually, I have to take 1 by resistance in parallel. Parallel is L by KA. But A is A1 plus A2. Total area is A1 plus A2 effective. On the right side, it is first one. 1 by L by K1A plus 1 by L by K2A. Oh, K1A1 plus K2A2. Okay. So I take the reciprocal. K into A1 plus A2 divided by L is equal to K1A1 by L plus K2A2 by L. I cut all the L's here and I get K as K1A1 plus K2A2 divided by A1 plus A2. That is a shortcut. Now these two equations are shortcuts. Okay, I was just proving them. You won't need the proof anyhow. But if at all you miss the equation, you forget the equation, you can formulate if you want. Just simple application of effective resistance in series and parallel in current electricity. You learned in current electricity. Look at this. This is the case when connected in series. When connected in series of same length and same area. Okay. This is the case when connected in parallel of same length but different area. These are the most commonly asked questions. But any question comes, you can do accordingly. 1 by RP is equal to 1 by R plus 1 by R2. 1 by RP is what? 1 by L by KA. K is K. K parallel I can put if I want. Into area is together it is A1 plus A2. On the left side it is always effective. A1 plus A2. Is equal to 1 by L by K1A1 for the first one plus 1 by L to K2, K2A2 second one. Take the reciprocal K into A1 plus A2 by L, K1A1 by L, K2A2 by L. All the L's are getting cut. You get K is equal to K1A1 plus K2A2 by A1 plus A2. So these are important equations. Like I told you, if two conductors are connected in series, the effective is 2K1 K2 by K1 plus K2. Very important. Okay. Number two, if two conductors are connected in parallel, if they have same area, same length, they'll give you like that only. Don't worry. Okay. K1A1 plus K2A2 by K1A1 plus A2 is the effective what do you call thermal conductivity. So you can forget about the method here. You just have to learn this equation. Okay. And I'm going to tell you one more thing. In this case, sometimes they might ask you to find this is temperature T1, temperature T2. They might ask you to find this temperature, intermediate temperature. So T is given by K1 T1 plus K2 T2 divided by T1 plus T2. Oh, K1 plus K2, K1 plus K2, K1 T1 plus K2 T2 divided by K1 plus K2. Okay, fine. K1 plus K2. That is how you find the intermediate temperature here, no? That's a shortcut. So there are three equations to be learned in this part. First equation is, like I said, K series. But there is a condition attached. Both the conductors are to be of same length and same area. So equation is 2K1 K2 by K1 plus K2. And if they are connected in parallel, same area in parallel combination is also possible. So if you put it, K1 plus K2 by 2 will be the answer. Okay. So if different areas are connected like this in parallel, different areas, they can even give same area. Answer will, you put A by 2, A by 2, A by 2. That's it. You will get K1 plus K2 by 2. Anyway, if they are connected in parallel, the equation is K1A1 plus K2A2 by A1 plus A2. And the third one, this is also very important. In such a case, you can use the direct method to solve it. I'll tell you how to solve it using direct method. But if they are of same length, which is most of the time, this is the case, you know, the temperature in the middle, temperature at the midpoint is given by K1 T1 plus K2 T2 divided by K1 plus K2. Did you understand? So we have seen the fundamental equations here, and we have a couple of more. One is, you know, what is specific heat capacity? Specific heat capacity. It is heat required. It is a heat required to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. For example, if you take 1 kilogram of water, 1 kilogram of water, okay, its specific heat capacity is 4,200 kilogram per 4,200 joules per kilogram per degree Celsius, per Kelvin. Okay, so that means you have to supply how much of heat? 4,200 joules of heat if you want to raise the temperature by 1 Kelvin or 1 degree Celsius. Okay, since it is temperature change, it can be even Kelvin or Celsius. You know, degree Celsius and Kelvin, temperature difference will be the same. You know that? Oh, tell me, this is 100 degrees Celsius. In Kelvin, it is what? 100 plus 273, T is 373. 200 degrees Celsius. In Kelvin, it is what? 200 plus 273, that is 473. Take the temperature difference, 200 minus 100, it is 100. 473 minus 373, that is also 100. So when it comes to the case of temperature differences, remember, not temperatures, temperature differences, both Kelvin and degree Celsius will have same value. Understood? Understood. When you talk about temperature differences or raising the temperature, it can be either Kelvin or degree Celsius. It won't make a difference. Understood? Okay. Temperature difference in Celsius is 100. Temperature difference in Kelvin is also 100. Understood? Okay, fine. So keep that in mind. Anyway, so what is specific heat capacity? Heat required to raise the temperature of 1 kilogram of substance by 1 degree Celsius. For water, it is 4,200. That means if you take 1 kilogram of water, and if you want to raise its temperature by 1 Kelvin, you must apply how much of heat? 4,200 joules of heat. Understood? Every substance has a unique value of specific heat capacity. So, what is specific capacity? Heat required to raise the temperature of 1 kilogram. What if it is 2 kilogram? Into 2, 3 kilogram. Into 3, 4 kilogram. Into 4. What if it is m kilogram? Into m. ms. So heat required to raise the temperature of m kilograms of substances, ms. And this is for 1 degree. What if it is 2 degree? Into 2, 3 degree, into 3, 4 degree, into 4, 10 degree, into 10, delta T degree, into delta T. This is the expression for heat required to raise the temperature of m kilogram of a substance by delta T degree Celsius. For example, you take, say, 20 kilograms of water, 20 kilograms. Okay. You want to raise the temperature by, say, 10 degrees Celsius. You know what is the heat required? You can use this equation. Amount of water, mass of water, that is 20 kilogram. You could put it here. Specific heat capacity, 4,200. You can put it here. Delta T, change in temperature. You can put it there. The unit is what? Q is heat. Heat is measured in joule by mass is kilogram, temperature in degree Celsius. Joule per kilogram per degree Celsius. Okay. Or joule per kilogram per Kelvin. Understood? I have a question here. What is the unit? Joule per kilogram per degree Celsius or kilogram, joule per kilogram per Kelvin. All right. So this is the amount of heat required. What have I written? What is specific heat capacity? It is different for different materials, right? Specific heat capacity is the heat required. It is what? It is a heat required. It is what? It is a heat required to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. So for m kilogram, you will need m times. For delta T degree Celsius, you will need delta T times. So it is what the heat required to raise the temperature of m kilogram of a substance by delta T degree Celsius is ms delta T, ms delta T. That is number one. Number two, there is something called latent heat, L. You know what it is? I'm taking ice at 0 degrees Celsius. Look at this ice at 0 degrees Celsius. This is ice. You know this is ice. It is at 0 degrees Celsius. What do I get if I heat ice now? If I heat ice, if I supply heat, can anyone tell me? If I supply heat, what do I get now? Will I get ice at 1 degree Celsius? Can you ever have ice at 1 degree Celsius? See, for ice, the melting point is 1 degree Celsius. That means the temperature won't rise until the last drop, last part of ice melts. Ice is totally melting. Then only the temperature will start rising. So ice at 0 degree Celsius gets converted to water at 0 degree Celsius. This is a phase transition, solid to liquid. Correct. Oh, tell me what? This process is called melting process. Reverse process is called fusion process. We will see this in detail later on in another chapter. Okay. This is ice at 0 degrees Celsius. Ice is solid. And then ice when heated, ice at 0 degrees Celsius, if you heat it, that's never going to give you ice at 1 degree Celsius. Ice won't raise its temperature because ice has to do something else there. What? Melt. Ice has to melt so as to become water. So it is totally converted to water at 0 degrees Celsius if you supply heat. This process is called fusion. This process is called melting process. The reverse process is called fusion process. That means freezing of water to become ice is called fusion process. Okay. Oh, sorry. That is freezing. This is called fusion process. Anyway, the heat required is called latent heat of fusion. Melting process is called fusion process. Okay. Melting process. I made a mistake while defining it. Okay. So latent heat of fusion. Latent heat of fusion is what? Heat required to convert 1 kilogram of ice to 1 kilogram of water. If you got 1 kilogram of ice, how much of heat has to be supplied so as to convert it to water totally, completely converted to water. Okay. Heat required for this is known as latent heat of fusion. This is for 1 kilogram, and for m kilograms it will be mlf. Okay. Similar way, if you take water at 100 degrees Celsius, look at this, similar thing happens. Water at 100 degrees Celsius, you supply heat here to water at 100 degrees Celsius. Okay, so it boils. You know, the boiling point of water is 100 degrees Celsius. That means the entire water, till the last molecule of water becomes vapor, you know, it never increases its temperature. Now we have what? Steam. We have steam at 100 degrees Celsius. So water at 100 degrees Celsius, when heated, becomes steam at 100 degrees Celsius. That is again a phase transition. This is called vaporization. This was fusion. This is vaporization. And we have something called latent heat of vaporization. Heat required to convert 1 kilogram of liquid to 1 kilogram of vapor. Okay, that is called latent heat of vaporization. That is for 1 kilogram, and for m kilograms it is mlv. I'll quickly repeat this one more time. These three equations are very, very, very important, and we will see these equations till the end of discussions on these 4 modules. Okay, right. Number 1, Q, heat required to raise the temperature of m kilogram of substance by delta T degrees Celsius is Q is equal to ms delta T. Then heat required to convert 1 kilogram of ice to 1 kilogram of water is latent heat of fusion. So heat required for m kilograms. If you want to melt m kilogram of ice to make m kilogram of water, heat required is mlf. Okay, and if the heat required to convert m kilogram of water to m kilogram of steam, water to steam is, that is mlv. So latent heat of vaporization is lv, latent heat of fusion is lf. Did you understand all these points? Go to the paper now. Question number 1. Read question number 1. 2 rods, one semicircular and the other straight, of same material and of same cross section. Okay, area are joined as shown in the figure. The points A and B are maintained at different temperatures. Read it again. 2 rods, one semicircular and the other straight, of same material and same cross-sectional area. Underline those points. Same material and same cross-sectional area are joined as shown in the figure. The points A and B are maintained at different temperatures. Points A and B are maintained at different temperatures. The ratio of heat transferred through the cross-section of semicircular rod to the heat transferred through the cross-section of straight rod. Look at this. You know, this is one rod. Okay, one semicircular rod like this. We have a semicircular rod, and then there is a straight rod like this. Okay, this is how it should be ideally drawn. All right, I'm drawing it here. Look at this. So we have two rods here. Look at this. We have two rods here. The figure is even the figure is given. Two rods, one of semicircular cross section and the other straight of same material. Same material means thermal conductivity is same for both. Same material means thermal conductivity will be same for both. They are made up of same material and same cross sectional area are joined. Same cross sectional area. Area here and area here are the same. Area here and area here are the same. Cross. They are talking about cross sectional area here, right? Cross sectional area is the same for both. Points A and B are maintained at same different temperatures. The ratio heat transferred, you have to find the heat transferred, right? Through a cross section of semicircular rod to straight rod. Semicircular rod to straight rod. So I can write the equation for heat transfer. What is dq by dt? Dq by dt is equal to K into A into TH minus TC. That is dt divided by dx. This is the modified version of our equation, right? Dt divided by dx. Okay. So they are asking you to find the heat transferred. So dq will be what? Cross multiply heat transferred. K into A into dt by dx into small letter t, dt. Okay. So I can find the heat transferred through semicircular rod. Look at this. K is same for both. Area of cross section is same for both. Temperature difference is same for both because this is kept at one temperature, TH. This is kept at another temperature, TC. The ends are together, right? The ends are together for this, right? So TH, the other end is at TC. So dt will be same for both. Time, they are asking you to find in a given time. Read the last word of the question. In a given time. So time is also same for both. So dq is proportional to 1 by dx. Or I could say dq for the semicircular rod by dq for the straight rod, semicircle by straight rod. Okay, that is the question. Is equal to dx for straight rod by dx for semicircle. They are an inverse ratio, right? Look at this. dq by dt. What is the equation for dq by dt? K into A into dt over dx. What I need is dq, the heat transferred. So the heat transfer will be what? Let us take this to the right hand side. K into A into dt by dx into d small t. And then K is same for both. They are made up of same material. This one and this one. No, both are made up of same material. Both are made up of same material. Area is same for both. Area of cross section. Look at this area of cross section is same for both. dt, temperature difference is same for both, right? Both are together here, both are together here, right? Then dt, small dt is also same. Then only thing that varies is dx. So dq is proportional to 1 by dx. So they are inversely proportional. So if I write the equation, they are asking you to find the ratio dq of semicircle to dq of straight rod. Should be inverse ratio, no? So dx of straight rod by dx of semicircle. What is ds for straight rod? ds for straight rod is actually 2 times radius. 2 times radius. dx means length of the rod. Length of this rod, straight rod, no? It is 2 times the radius, diameter, right? It actually looks like the diameter of a circle, right? And for the other one, this is what? Length of semicircle is what? It is pi r. Because full circle it is 2 pi r, semicircle it is pi r. See, dx of straight rod, length of straight rod is 2 times radius. So 2 times radius by dx of semicircle is pi r. Full circle it is 2 pi r, semicircle it is pi r. R and R are cut, you're getting 2 by pi. So the answer is 2 by pi. 2 by pi is there in the question. Option A. Did you understand? Moving on to the next question. See how many times it's asked. It's a previous, what do you call, CPMT question. That means NEET question. Many times asked in other examinations also. For cooking the food, which of the following type of utensil is most suitable? Okay, so I take a pan. This is a pan, frying pan. Okay, right, frying pan like this. Okay, and usually frying pan's bottom should have what all characteristics? Frying pan. You know, we put the food on top of it, right? And you know, the flame is put below this, right? So heat should be conducted, right? Maximum heat should be conducted. So what do you think about conductivity? Conductivity should be very large, as large as possible. That is why you use copper. You can use gold for it because gold is the best conductor. Can you make cooking utensils gold? You can't afford to have it, right? So this is why next candidate is silver. Silver is also better than copper, but even silver is expensive. Okay, you know, some people are using silver cookwares, right? Cookingwares, right? Anyway, the bottom should be having as much of conductivity as possible. Gold is the best conductor. You can use gold or silver, or then comes copper. That is why cooking utensils have their bottom made up of copper. Copper has large conductivity. K is large. Then they talk about specific heat capacity, right? How about specific heat capacity? That should be small because specific capacity is small. One second. Specific capacity is low means what? Specific capacity. Read the options: high specific heat and low conductivity. High specific heat and high conductivity. Low specific heat and low conductivity. Low specific heat and high conductivity. Okay, so it should have low specific heat as well. Why? Because specific heat is what the heat required to raise the temperature of 1 kilogram of substance by 1 degree Celsius. It is low for this because if it is large, it will take longer time to heat up the pan. The pan is to be heated up now, it will take longer time. Just imagine the specific heat capacity is large. Just imagine what if specific heat capacity is large. That actually means you have to supply a lot of heat to heat the pan up, right? Correct. See, when you put the pan on the fire, you know, initially the pan gets heated up first, then you'll put the food on top of it, right? The pan heats up first, right? So if the pan is to get heated up very quickly, which is your requirement, so as to save fuel, if you want to save fuel, you need the pan to get heated up as early as possible, as quickly as possible. And that happens when specific heat is low. So here the answer is, that question has been asked 1, 2, 3, 4, 5, 6, 7 times so far. Answer is low specific heat capacity and low conductivity, sorry, high conductivity. So answer is option D, low specific heat and high conductivity. Did you understand? So question number 2, for cooking food, you know, like I said, for cooking food, my intentions are what? Conductivity, you know, maximum heat should be conducted. So conductivity should be large. Apart from this, you put the pan on the fire first, and the pan has to get heated up first. So it has to get heated up very quickly, means low specific heat should be there, because, you know, if it is large, specific capacity is large, you need to supply large amount of heat to heat it up, right? Okay, so answer is option D. Question number 3 is very important. This is a previous IITJEE question, but before that, I'll tell you something. You know, hope you know this. You might have heard this. 1 joule is 4.2 calorie. Calorie CGS unit. Have you heard about it? Oh, the other way, sorry. 1 calorie. 1 calorie is 4.2 joules. 1 calorie is 4.2 joules. 1 calorie is 4.2 joules. Okay, I made a mistake, sorry. 1 calorie, calorie CGS unit and 4.2 joules. And let us read the question now. Just keep that in mind. A room is maintained at 20 degrees Celsius by a heater of resistance 20 ohm connected to 200 volt mains. Okay. A room is maintained at 20 degrees Celsius. So we have a room here. I'm just drawing it. This is a room. Okay. This is a room, and the room has a heater inside, like a heater inside. This is a heater, right? There is a heater inside. A room is maintained at 20 degrees Celsius. So inside temperature is 20 degrees Celsius. Room is maintained at 20 degrees Celsius by a heater of resistance 20 ohm. Heater resistance is 20 ohm. Heater resistance is 20 ohm connected to 200 volt mains. Voltage is 200 volt. Okay. So we've been given everything. Read it again. A room is maintained at 20 degrees Celsius. So room temperature is 20 degrees Celsius. And it is heated by a heater of 20 ohms. Heater of 20 ohms. It's heated by a heater of 20 ohms. And the voltage is 200 volt. The temperature is uniform throughout the room. Temperature is uniform throughout the room, and the heat is transmitted through a glass window. Heat is transmitted. There is a glass window over here, right? Heat is transmitted through a window of area. Area how much? 1 meter square, and thickness. Thickness is given. Thickness is taken as L. L is how much? L is 2 centimeters, right? Oh, sorry, 0.2 centimeters. L is 0.2 centimeters. Area is 1 meter square. Area is 1 meter square, and just give me a second. 0.2 centimeters. 0.2 centimeters can be converted to 0.2 into 10 power minus 2. Okay. Then what will be the temperature outside? Temperature outside is to be calculated. Temperature outside. Okay. Then given the thermal conductivity is 0.2 calorie per meter per degree Celsius, and joule is 4.2 joule per cal. 1 joule is 4.2 joules per calorie. 4.2 joules will be 1 calorie. That is given. Read the question carefully. A room is maintained at 20 degrees Celsius by a heater of resistance 20 ohm connected to 200 volt means the temperature is uniform throughout the room and heat is transmitted through a glass window. Heat is transmitted through a glass window over here, and thickness is 0.2. Thickness is just give me a second. Thickness is 0.2 centimeters. Okay, 0.2 centimeters. What will be the temperature outside? Given thermal conductivity is given 0.2 calorie. Thermal conductivity is given 0.2 calorie per meter per degree Celsius. Okay, calorie per meter per degree Celsius second. Okay, given that thermal conductivity, and then okay, fine. So let us see the question now. See this. What does the question? It's a difficult question. It's an advanced level question. You know what do we have? We have a room here, and then there is a room heater inside. Which means what? Room heater inside means outside temperature is less because heater is used in cold countries, right? Heater is used where? Heater is used in cold countries, right? Do they say anything about it? Nothing. Okay. So heater is, let us take this temperature as say theta. Temperature is theta. Heater is used in cold countries. So this must be a cold country, and outside temperature is less. So tell me what? Heat is being generated here inside. Heat is being generated inside, and heat is transported through where? Heat is transported through the window only. Heat is transported through the window. Correct. So what is the heat generated? Heat generated, I could say it is V square by R into T. Do you remember this? Heat generated, I can write equations independently. What is the heat generated inside? Heat generated inside is V square by R into T. V square by R into T. Why did I write this? This is called Joule's law of heating. Heat generated is given by I square RT, or V square by R into T, or V into I into T. There are 3 equations for it. Okay, Q, heat generated is V square by R into T. All right. I use this equation because V is there, R is there. Now this is the heat generated, and the generated heat is transported through the window, right? It is transported through the window. What is the heat transported through the window? What do you call transferred? Heat transferred is equal to how much? K into A into T hot minus T cold divided by L into T. Where do I get that T from? This was actually Q by T, dQ by dt. Do you remember? Do you remember the equation? Oh, tell me what was the equation for heat transferred? We wrote it, dQ by dt. Don't you remember? Q transferred. dQ by dt was K into A into TH minus TC by L. Don't you remember? Then I take T to right hand side, time to right hand side. Time was on denominator, I take the right hand side. And at steady state, what happens? Whatever heat is generated is transported through the window. So I can say at steady state, Q generated is equal to Q transferred. Okay, because heat is transported through the window only. Remember that point. Okay. So let me put it one more time. There is heat generated inside the room. Okay, by what? By the heater, and that heat is transported through the window. So heat generated is transported through the window. Okay, that is how the temperature is maintained in the room. Excess heat generated is transported. So heat generated is V square by R into T. and that is transported through the window. Heat transported is what? K into A into TH minus TC into T divided by L. You have to ask me now if you have any questions. Okay, Q generated is equal to Q transported. And then I can equate these two, V square by R into T. V square by R into T is equal to K into A into TH minus TC, TH minus TC into T divided by L. So T and T are cut. Okay, what do we get? T and T are cut. So I have an equation V square by R. Now before doing this, I'll do something. Conductivity is given in what? Look at this, 0.2 calorie per meter per degree Celsius per second. Calorie, no? So it is better to have the left side also in calorie. This is already in joule, right? Because SI system has been used all along, right? So it is better to convert this to joules, sorry, calories. So I'm dividing with 4.2. Why? Look at this. 1 calorie is 4.2 joules. So 1 joule will be what? 4.2 goes to denominator, 1 by 4.2 calorie. Okay, 1 by 4.2 calorie. Understood? 1 calorie is 4.2 joules. So 1 joule will be 1 by 4.2 calorie. So left side is already in joule. If I want to convert that to calorie, why do I insist on converting to calorie? Because the other side is having a calorie, right? Calorie and calorie can get cut. Otherwise, it's converting calorie to joule is very difficult. Conductivity is very difficult. Understood? They never expect you to do that. Understood? Instead, it is better to convert. The left side is already, that is in joules. Joule is to be converted to calorie. How do you do that? 1 joule is 4 joules is 1 calorie. So 1 joule will be 1 by 4.2 calorie. So 1 by 4.2, you have to multiply with. So I'm putting the value 1 by 4.2 into V square, that is 200 into 200 divided by resistance, that is 20, is equal to thermal conductivity 0.2 into area 1 meter square into TH minus TC. Hot temperature of hot junction is 20, outside temperature is theta. Cold temperature 20 minus theta by length is 0.2 into 10 power minus 2. Length means thickness of window. Actually, it is through the window that the heat is transported. So 0.2 and 0.2 are cut. Tell me what you got. 20 and 200 are cut. This is 10. So this is like 2000 divided by 4.2 is equal to 20 minus theta into 10 raised to minus 2 goes to numerator, 10 raised to 2. 10 raised to 2 is getting cut with 2 zeros here. So 20 by 4.2. You have to be very precise and calculating it. 20 by 4.2. So this is how you get it. 20 by 4.2 is 20 minus theta. So 20 by, if you take 4, 20 by 4 it is 5. I won't need calculator. I won't need. 5 is equal to 20 minus theta. Theta goes this way. This is 20 minus 5. That is equal to 20 minus 5. That is equal to 15. And when you check the options, there is a catch. There is a trap here. I'll tell you. Since it's an ITJE question, 15 degrees Celsius you see there. But there is a more correct option. Look at this. If you take precisely this 4.2, no? If I've taken it as 4, but if I take precisely, this value will be, this is greater than 4. So it will be less than 5. Say 4.5 something. 4.5 or 4.6. Okay, when you take it to right side, 4.6, it is like 15.4. So there is a better option. Answer is option A, 15.24 degrees Celsius. Did you understand? So this is the concept. Heat is generated inside, heat is transported through the window. The heat generated inside is given by V square by R into T. That is called Joule's law of heating. And then heat transported, we learned an equation for it. Heat transported per second, dQ by dt. But dt is taken to right side because they are asking you to find dq. So K into A into Ts minus Tc by L into T. And at steady state, Q generated will be equal to Q transported. There is only one way by which heat can be taken out. Once there was a question like, what is the heat? What if the entire wall, I mean, all the walls are heat conducting? So you have to take 6A square as area. One side is square, no? Look at the wall in front of you. You're sitting in a room right now, right? Look at the wall in front of you. That is A square. A into A square, no? A square. 1, 2, 3, 4, 5, 6. There are 6 surfaces. So area has to be taken 6a square. But fortunately, they have said like heat is transported through the window only. So window area alone is to be taken. So it is what? The other areas, other walls are perfectly insulating. That is why only heat is transported only through the window. Okay. But there was one question, like I said, all the walls are conducting. Understood? Then you will take the whole area. Okay. But here, fortunately, we have only window area. Anyway, I'm just putting the value V square by R into T is equal to K into TH minus TC into T divided by L. And I have to, this is in joules, but it's better to get it in calorie. Why? Because right side is having K, which is given in calorie per meter, calorie. Okay. So left side is also, it is desirable to have left side in calorie rather than having right side in joule per. Okay. This converting this to joule is really difficult. Okay. So it's better to have this in calorie. For that, 1 joule is 1 by 4.2 calorie. So 1 by 4.2 you have to multiply. Okay. And then dividing, you get, simplifying, you get something like this. 20 by 4.2 is equal to 20 minus theta. Usually in entrance examinations, you approximate, you take it as 4. 20 by 4 is 5. Take it this way, 20 minus 5 is 15. When you see option B is there, but that is wrong. That's a trap actually. Here you can't approximate, it is 4.2 itself. So when you divide with 20 with 4.2, it is little greater than 4, no? So greater than 4 means the value will be less than 5. It's say, let us say it is like 4.7. Okay, you have to calculate precisely, but anyway, you can approximate. It's little, since this is, if it is exactly 4, answer is 5. But it is greater than 4, answer is less than 5. And take it right hand side, 4.7. 20 minus 4.7 is 15.3. So there is a more precise answer, 15.24. Answer must be option A. Did you understand now? So we have done till question number 3. Question number 4 and question number 5 are homeworks for you. Try them at home. If you don't get, I'll help you tomorrow. Question number 4, that's an easy one. 5 is also a relatively easy one. That's a repeated question. Question number 6. Let us look at 6. That's an important question. 3 rods made of same material and having same cross section. Remember, question number 6. 3 rods. Remember, 3 rods of same material. Same material means thermal conductivity is same for all. And same cross section have been joined as shown in the figure. Each rod is of same length. So there are 3 things given. I have 1 rod here. Okay. I have a second rod here. Repeated question. I have a third rod here. Okay. Now what all things are given? All are having same length, right? Same length. L. All are having same area. All are made up of same material. Okay. So K is also same. The left and right ends are kept at 0 degrees Celsius and 90. Left end is kept at 0 degrees Celsius and the right end is kept at 90 degrees Celsius. This is at 90 degrees Celsius. What is the question? Will be intermediate temperature. The temperature of the junction of the 3 rods will be. The temperature of the junction is to be calculated. This is the junction. I need to find the temperature of the junction. Okay. Temperature of the junction. Look at this. I got what? I got 3 conductors joined together like this. All the conductors have same length. L. Same area. A. All are having same area. And the temperature here is 0. Temperature at this end is 90. Intermediate temperature T is to be calculated. Now you can apply Kirchhoff's junction law here. Do you remember Kirchhoff's junction law from current electricity? You know, you can take this as a higher potential. This is called temperature potential. Degree Celsius, I mean, temperature can be called thermal potential. This is thermal potential, no? Just like you having electrical potential, we have thermal potential. Higher thermal potential, higher thermal potential. This is lower thermal potential. This is much lower thermal potential. So there is a current, heat current flowing this way. I1, I can call I1. There is a heat current flowing this way, I2. And together they flow to the left, I3. So there are 3 currents here, no? Why does the current flow this way? Why can't the current flow this way? Tell me. Because that temperature is higher, that potential is higher. But see, current always flows from higher potential to lower potential. Or water always flows from higher level to lower level, right? You take 2 buckets of water with different levels. Just imagine you take 2 buckets of water with different levels of water. And if you connect them, water flows from higher level to lower level. Similar way, current flows this way because this potential is higher than this potential. Okay, similar way, this potential is higher than this potential. 90 is greater than T. You are going to get something like in between 90 and 0, this temperature. Understood? finally. That is intermediate temperature, right? So I1, this is I1 coming here, this is I2 coming here, this is I3. What does Kirchhoff's junction law say? The algebraic sum of currents reaching any junction is equal to 0. The algebraic sum of currents reaching any junction is equal to 0. So incoming current I1 plus incoming current I2 should be equal to outgoing current I3. This is what Kirchhoff's junction law. According to KJL, Kirchhoff's junction law, the incoming current I1 plus incoming current I2 should be equal to outgoing current, because current can never stop flowing. Current has to keep flowing. Current cannot stop anywhere. Current can never get accumulated anywhere. Current has to keep flowing. So I1 is coming in, I2 is coming in. Together they join and then flow as I3. I1 is equal to I1 plus I2 is equal to I3. What is I1? I1, I can say it is 90 minus T divided by R plus Y. Current is potential difference by resistance V by R. Am I correct? Oh, tell me what? Current is what? Potential difference divided by resistance. For this part, what is potential difference? Thermal potential here is 90. Thermal potential here is T. You know, there I was using electric potential. Here it is thermal potential 90, thermal potential T. So thermal potential difference is 90 minus T divided by resistance is R. For this one, it is what? Thermal potential here is 90, thermal potential here is T. So thermal potential difference is 90 minus T. There also resistance is R, because conductors are of same length, same cross section. They are identical in all senses, right? Is equal to, for this one, tell me, thermal potential here is T, thermal potential here is 0. So T minus 0 divided by R. Even there, resistance is same. Resistance here will be same. Why? Because resistance, thermal resistance, do you remember L by K? Length is same for all. K is same for all. All are made up of same material. A is same for all. All are same, identical, no? So you can cut these T's. This is 90 plus 90, 180. T minus T is equal to T. These T's goes to the right side. So there are 3 T's on one side is equal to 180, or T will be 180 by 3. That is equal to 60 degrees Celsius. There are many ways to do this question, but this is the easiest one. It's like a shortcut. You know, answer is option B. Second option is correct. Did you understand? So this is an important question. This is temperature here. That is thermal potential. I can call it thermal potential. Just like electric potential is there. 90. Thermal potential here is 90. Thermal potential here is T. Thermal potential here is 0. Kirchhoff's junction law says what? Incoming current plus incoming current is equal to outgoing current. I1 plus I2 is equal to I3. I is V by R by Ohm's law. V by R. So what is potential difference? 90 minus T by resistance R. 90 minus T by resistance R. T minus 0 by resistance R. All are having same resistance, because resistance is L by K. We learned this, right? L is same for all. K is same for all, same material. A is same for all given in the question. So R's are same. You are getting them cut, and then T will be equal to 60. We have a couple more questions to go. Question number 7, question number 8. Okay, read question number 7 here. Read question number 7 here. A cylinder, it's a previous IIT question, but that got repeated 3 times later. It's an important one. A cylinder of radius R made of material of thermal conductivity K1 is surrounded by a cylindrical shell of inner radius R and outer radius 2R made of thermal conductivity K2. So let us draw the figure. This is a cylinder of thermal conductivity K1, and then surrounding this, there is another cylinder of thermal conductivity K2. Draw the figure and tell me. I'll explain. Read the question now. What is given? A cylinder of radius R. The cylinder, the inner cylinder has a radius R. Okay, made up of a material of thermal conductivity K1. So the inner cylinder has a radius R and thermal conductivity K1. It is surrounded by a cylindrical shell of inner radius R. Its inner radius is R and outer radius is 2R. Okay, it's inner. That means it perfectly fits outside this, no? Okay, its inner radius is R and outer radius is what? Inner radius is R and outer radius is 2R. Okay. The two ends of the combined system are maintained at 2 different temperatures. This is at hot body temperature. This is hot temperature. This is cold temperature. No. Okay, TH and TC, they are maintained different. There is no loss of heat across the cylindrical surface and the system is in steady state. That is understood. There is no loss of heat. There is no loss of heat through this. Heat only is transported towards the right. Okay, read that statement. That is an unwanted statement for us. Right. The two ends of combined system are maintained at two different temperatures. There is no loss of heat across cylindrical surface. Cylindrical surface. This is cylindrical surface, no? Cylindrical surface, right? Across cylindrical surface. See this? This is the conductor, no? This is the conductor, okay? Across cylindrical surface, no heat is transported. Heat is transported through the circular surface only. Okay. And then what is the question? What is the question? System is in steady state. Effective thermal conductivity of the system is. I have to find effective thermal conductivity. I would say that these are in parallel combination. These are in parallel combination. How do I assert that these are in parallel? Can you tell me how? For both the cylinders, that means the inner cylinder and the outer cylindrical shell, left ends are connected together. Look at this, left ends. Left ends. Where is left end? For both, left ends are at H. Oh, at TH. Left ends are at TH. Right ends. Right ends. Tell me about right ends. Right ends are at TC. Right. So, for both the cylinders, for the inner cylinder and even the outer cylindrical shell, the left ends are joined together. Right ends are joined together. Such a system is called a parallel combination. Where is the left end for the cylinder? TC, TH. Where is the left end for the shell, cylindrical shell? That is also TH. Where is the right end for the cylinder? TC. Where is the right end for the cylindrical shell? That is also TC. Okay, so this is a parallel combination. You remember, for parallel combination with the same length, do you remember the equation I gave a shortcut? K1A1 plus K2A2 divided by A1 plus A2, A1 plus A2, A1 plus A2, K1A1 plus K2A2 divided by A1 plus A2. This is what I gave for parallel combination if they have same length. Hope you remember. So let us write A1. First area is what? Look at the shaded area, it is pi r square. A1 pi r square. Second area is what? Second area you have to be very careful. Okay, for the outer cylindrical shell, the area is what? Pi into 2r the whole square minus pi r square. Why? Because look at this. Look at this. The silver color, no? The white color you see? The white color area you see this? That is pi r square. Do you see this or not? Tell me. Do you see an inner cylinder here? The white color, that is pi r square. And for the bigger one, it is pi into 2r the whole square. Pi into 2r the whole square because the radius is 2r. And I need the area of this black portion, area of the black portion only. See this, the area of the black portion to get the ring, area of the ring. Okay, so I can shade it with something else. This is, I'll keep this unshaded. Okay, I'll tell you the required area now. The required area I'll shade. This is the area needed. So what is the area there? What is the area there? Outer ring square, outer area minus inner area. So pi into 2r the whole square minus pi r square. 2r the whole square is 4r square, 4 pi r square minus pi r square, 3 pi r square. So let us put it. K1 into area 1 pi r square plus K2 into area 2 3 pi r square divided by pi r square plus 3 pi r square. So this is what? This is, I can take pi r square on numerator common. This is K1 plus 3K2, K1 plus 3K2 by pi r square plus 3 pi r square, 4 pi r square. Pi cut, r square cut. You will get K1 plus 3K2 plus 4. It's a previous IIT question and the options are not given. Answer is this, K1 plus 3K2 by 4. Did you understand? So one more time, because look at this, both the cylinder and the cylindrical shell have their left ends at TH, have their right ends at TC. So they are in parallel combination. For parallel combination with same length, the equation is K1A1 plus K2A2 divided by A1 plus A2. A1 is area of the inner cylinder, which is pi into r square. It is circular, right? But for area of outer cylinder, be very careful. It is actually pi into 2r the whole square. That means the whole area, 2r is the radius, right? Minus inner cylinder surface area, cross-sectional area, pi r square. So that makes it 3 pi r square. Put them here, k1 a1 into pi r square plus k2 a2, k2 into 3 pi r square by a1 plus a2, pi r square plus 3 pi r square. So if I take pi r square common, I'll have k1 plus 3k2 on numerator. Pi r square plus 3 pi r square is 4 pi r square. Pi r square gets cancelled out on numerator and denominator. That leave you with k1 plus 3k2 by 4. Options are not given. Okay, let us move to question number 8. We will wind up with this question for the day. Read question number 8 there. Question number 8. What is given in question number 6? Identical. That's again a repeated question. 6 identical rods are joined as shown in the figure. Points A and D are maintained at temperatures 200. Draw the figure. Draw the figure. 6 identical conductors. Now 6 conductors are there. Draw the figure. 6 identical conductors. This point is A. This point is B. And this point is C. And this point is D. 6 identical conductors are there. Okay. Temperatures are 200 degrees Celsius here. This is 20 degrees Celsius. And you've been asked to find temperature of junction B. Tell me when once you're done drawing this. Okay, right. So how many conductors are there? How many conductors are there? 6 different conductors are there, right? 6 different. 1, 2, 3, 4, 5, 6 conductors. Temperatures are 220. N temperatures are given 200 degrees Celsius and 20 degrees Celsius. See this? I can convert this to resistors. Look at this. My first resistor. This is AB. This is A. This is B. Right here I have B. And then what? I have a resistor here. I have another resistor here, another resistor here, and a fourth resistor here. Then there is a resistor here. Okay. This is D. This is C. And this is B. This is R, 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 R. All are equal resistances, right? So let us redraw the figure now. Tell me, A. First resistance is intact. I'm not touching it. This is A. Now this point is B. All right. And what about these two? These two are in what? These two resistors are in what? These two resistors. Can anyone tell me? Can anyone tell me what is the kind of combination they are in? They are in a series combination. Am I correct? I'm expecting everyone to answer. Tell me why. These are in series combination. Am I correct? Similarly, these are in series combination. R plus R2R, R plus R2R. And they are in what? These two. Tell me. 2R parallel 2R. This is 2R, this is 2R, right? Look at this. This R and R are in series. No, Wheatman's principle is not to be applied. It is simpler than that. Why should you apply Wheatman's principle? That is not needed. R and R are in series. R and R are in series. So R plus R is 2R. R plus R is 2R. So 2R and 2R parallel. Effective is what? 2R into 2R by 2R plus 2R. Do you remember R1 R2 by R1 plus R2? So what is that? 2R into 2R. 4R square by 2R plus 2R. 4R. Answer is R. So in place of the whole setup, I can put 1R. Okay, instead of the whole thing. And then comes point C. Then the last resistance. That is also R. This is 200 degrees Celsius. This is 0 degrees Celsius, right? Oh, 20 degrees Celsius. Did you understand till this point? Okay, so we have how many conductors here? 1, 2, 3, 4, 5, 6. And I'm reducing this circuit. You know, I'm taking resistances in place of this. This is a resistance, thermal resistance, thermal resistance, thermal resistance, resistance. All are identical. And these two, if you take, are in series. R and R are in series. They come one after the other, right? R plus R. That is 2R. Series is R plus R. This is R plus R. That's again 2R. And 2R and 2R, there are multiple paths here. Current can flow along two different paths. So 2R and 2R in parallel. What is effective? R1 R2 by R1 plus R2. R1 R2 by R1 plus R. You've been learning since class 10. 2R into 2R by 2R plus 2R. So 2R into 2R, 4R square. 2R plus 2R, 4R. 4 and 4R cut, R and R cut, you're getting R. So instead of the whole thing, I can simply put an R. That's it. So this is my reduced figure. Is that clear now? First resistance intact, last resistance also, it is kept like that, and then the middle resistance alone is replaced with an R. Now tell me, you can call the temperature as TB, temperature as TC. Okay. So what is the temperature difference here? What is the potential difference here between A and D? What is the potential difference between A and D? What is the potential difference between A and D? 200 minus 20. Potential at 200. Potential at A is 200. Potential at D is 20. 200 minus 20 is 180 volts, right? Those 180 volts will be uniformly spread along 60, 60, 60 along the three resistors. Did you understand? No. I'll tell you. You know, what is the potential difference between the first point and last point? The potential here is 200. I'm talking about thermal potential, which is called temperature. Thermal potential or temperature. The thermal potential or temperature here is 20. So what is the potential difference between them? The endpoints. Potential difference is 200 minus 20, 180. So those 180 volts will be equally spread across the three resistors. Why equally? All are identical. So 180 divided by 3. 180 by 3 will be 60, right? So 60 will go here, 60 will go here, 60 will go here. So 200 minus 60 will be what? This temperature will be 140. 140 minus 60 will be what? This temperature will be 80. Then 80 minus 60, this temperature is 20. So the question is to find temperature of B, that is 140. Answer is option C. Did you understand? So look at the temperature difference here. Look at this. You know, I've taken the temperatures here. I've taken the temperatures here. The temperature at the end points are, the temperature here is 20. The temperature here is 200. Temperature here is 20. So what is the potential difference then? VAD is equal to VA minus VD. Higher potential minus lower potential. So between the end points, the temperature is to be, potential difference is to be calculated. 200 minus 20. That will be 180 volts. 180 volts. Okay. 180 volts. So VAD, how many resistors are there? 1, 2, 3. So this voltage should be uniformly spread among those because they are identical. 180 will be divided equally among the three guys. One resistance, second resistance, third resistance. So 180 by 3, that is equal to 60. So each resistance gets 60. So this resistance gets how much? 60 volts on it. This resistance gets how much? Again 60 volts on it. And even the last one gets 60 volts on it. So 200, 60 gone here, no? So 200 minus 60, this temperature will be what then? 140. 200 minus 60 is 140. Then 140 minus 60, this temperature will be 140 minus 60 is 80. Then 80 minus 60, that is 20. Already it is there. They are asking you to find the temperature here. So the answer is 140, option C. But if they ask you to find the temperature here also, you have the answer. It is 80. Did you understand now? That's all for the day. We'll continue tomorrow.